this chapter, we're going to study different statistical distributions. In this lesson, we're just going to work through some applications of the normal distribution curve.
Okay, so in this little lesson here, what we're going to do is we're going to take a look at just some applications of the normal distribution curve. There's just going to be a handful of applications that we're going to look at some questions. I'm going to show you the use of the calculator in doing that, just some things to watch out for. The real trick to remember here is that when you're looking for the probability of events happening, of a group of events happening, what we're really looking for here is the area under the normal distribution, okay, the normal curve here from, let's say, m to n here. So the total area under the curve is going to be 1. Okay, that's key here, right? The total area is 1. And that makes sense because the maximum probability that you can have for an event is going to be 1, right? If it's 1, you're 100% it's going to happen. So when you add up all the probabilities of all the possible events here, that's going to end up being 1 here. So the number of successes divided by the number of outcomes is going to equal the area divided by 1, which is just going to be the area under the curve. And remember that the tool that we have for this is that normal CDF on the calculator. Okay, where we've got the left bound, the right bound, the mean, and then the standard deviation. Now, let's just go through and do some problems so that you can see how this works. Okay, so here's our first question here. It says, the life of a particular lawnmower engine is normally distributed with a mean of 8 years. Okay, mean is 8, and a standard deviation of 2 years. Here we go. So now find the probability that an engine will last between 7 and 10 years. Answer correct to 4 decimal places. Okay. So first of all, we know that the mean here is at 8. And so we're interested in 7 to 10. So I'm interested in this area right here. And that's going to be the probability. So our probability is going to be the normal CDF. Our left bound is going to be 7. Our right bound will be 10. Now, because we're not talking about a standard normal curve here, we're actually talking about data that hasn't been normalized. Our mean is 8 and our standard deviation is 2. So on my calculator, that's exactly what I'm going to do. So second vars to get into the distribution, I go to the normal CDF. My low bound is 7. My right bound is 10. But this time my mean is 8 and my standard deviation is 2. So for some of you, this is what it's going to look like when you enter that in your calculator, and then I press enter, and I get 0.5328. Okay, so the probability is 0.5328. Okay, now this is what probability looks like, by the way. As soon as you convert it into a percent, you're actually answering that question slightly differently. So don't do that. Probability should be a number from 0 to 1. Now let's take a look at the next one. It says find the probability that an engine lasts more than 10 years. Okay, well here's 10. Again, I know that the mean is 8 and I know that my standard deviation is 2. So my probability is going to be, again, the normal CDF. This time though, the low bound here is 10. Okay? Now, what we have done in the past here is used to tell the calculator that I want you to go to infinity. What we'll do here is go 10 to the 99, and then the mean is 8 and the standard deviation is 2. And the calculator gets that. So let's go back into this. Okay, second vars normal CDF. My low bound is 10. This time my upper bound is going to be 10 to the 99. Now there's a couple of different ways you can do that in your calculator. I know that some people use like the engineering notation here, the EE. It doesn't matter. That's all good. Mean and standard deviation stayed the same. Press enter, and I get 0.1587. Okay, 0.1587. So there's almost a 16% chance, okay, that something is going to last longer than 10 years. And notice how I said that. As soon as you convert it to percent, it's really interpreted more as, or called more, it's called chance. Sorry, I don't know why I stumbled over that. Anyway, next one. The company guarantees that the engine will last at least 6 years. Okay, so here's 8. will last at least 6 years. So if 10,000 engines are produced in a year, how many should they expect to replace under the warranty? Okay, well, wait a minute. Here's the 6. They're not going to replace these ones up here. They're going to replace these ones down here. So what we want to do here is we want to figure out what this area is as a probability and then multiply that by the number that are produced here. So the number produced are going to, the number that we have to replace, okay, the number that we have to replace is going to be the number that were produced, okay, multiplied by the probability. Oh, gee, I've got too many of these here. So the probability of being from like 0 to 6, or actually I shouldn't say it like that. Because of the way the normal curve works, we don't actually want to do it like that. Not from 0 to 6. I want to be the probability that its lifespan here is less than 6. Okay. I know that it doesn't make sense to talk about the lifespan of an engine that goes into the negatives. Totally get that. But this is an approximation, and this is what the curve needs. So the number produced is going to be 10,000 multiplied by the probability. I will get that by going normal CDF. And now, once again, I recognize that it doesn't make sense to talk about the negative lifespan of an engine here, particularly if I go negative 10 to the infinity. That makes no sense at all. However, that doesn't matter. The right bound will be 6, the mean is 8, the standard deviation is 2. So we're going to multiply the number produced by the probability that it falls in that area there, that region. So here we go. 10,000 multiplied by the normal CDF, negative 10 to the 99. Again, don't let the fact that that's a weird thing throw you off here. This is an approximation. Okay, up to 6, 0, 0. It fills that in. And that company can expect to, now we're going to round this to the nearest whole, so this is going to be 1587. Can expect to replace 1,587 engines. Okay, that's what they can expect to replace. Let's keep going here. Still talking about these engines here. So what guarantee should the company offer so that less than 5% of the engines are returned? Now that's interesting. Less than 5% are returned. So now I'm asking the question in a slightly different format. What I want to know is if this is 8 and the standard deviation is 2, I want to know what is this value here if this area here is 0.05. So I'm going to replace everything in this region right here. I want that to be less than 5 engines that last, less than 5% of the expectation here. Well, to go backwards to find that, and let's call this our lifespan here, or well, we'll call this L. L is going to be the inverse norm of that area, 0.05, comma 8, comma 2, the mean and the standard deviation. Okay, so this time we know the probability. We're just going backwards here. So, whoops, wrong button. Into my distribution menu, go down to inverse norm, 0.05. There's my 5%. Okay, and remember that's up to 5%. But my standard deviation is 8, and my mean is 8. My standard deviation is 2, is what I meant to say. And, okay, now I get 4.7. So I'm going to write this out here as approximately 4.71029 ... Now the thing is, if I round that up to 5, okay, as a warranty, so they're going to guarantee this for 5 years, that means I'm going to be replacing more than 5% of those engines. So what I'm actually going to do is my guarantee here is only going to be for 4 years. I am going to round that down, okay, to get my warranty. I hope that makes sense, because that kind of rounding is a little bit weird, but I don't want to be replacing more than, and that's why the question is worded the way it is, so that you are replacing less than 5%. The next one. If 90% of the engines will last less than, 90% of the engines will last less than how many years? Okay, this is called the 90th percentile since 90% of the data is below it. So we'll answer it correct to one decimal place. So here we go. We're going to drop this line here. Our mean is 8. Our standard deviation again is 2. I'm looking for this value right here. Okay, we'll call that L again for lifespan, where this is going to be 0.9. And that is going to be, once again, the inverse norm. But this time it's going to be 0.982. Go to the calculator. Down to inverse norm, 0.982. And 10 point, now to the nearest tenth, okay, to the nearest tenth. And in this case here, that's all it wants. It's not giving us any indication of how to round it or anything like that. So we're just going to round to the nearest whole here. So 10.6 years. Okay. So if your particular engine there lasted more than 10.6 years, you are beyond the 90th percentile. It really lasted a long time. And then finally, out of this little section here, between what two values will 90% of the data be symmetrically located about the mean? This is called the symmetrical 90% confidence interval. Okay, so what I'm looking for here, I'm looking for the two data values here, L1 and L2, such that in between here and here, and remember this is 8 and my standard deviation is 2, in between here and here, this is going to be 0.9. Well, okay, that will occur when these individual pieces here are 0.45, 0.45. Now, if 90% of the data falls in between those two, that means 10% are out here. And since this is symmetric, that means this is 5%, and this out here is 5%. Okay, so to get L1, I'm going to use the inverse norm of 0.05, comma 8, comma 2. Okay? And the nice thing is I had already done that. That was up here. Because remember in question D here, we were only going to replace that 5%, so away we go. So I already know that this is going to be 4.7. Approximately 4.7 to that nearest tenth there. L2, on the other hand, is going to be the inverse norm. Well, it's not going to be 90. In between these two is 90, but there's this little bit more here. So that means this is going to be from the left, far left, all the way up to this point is actually going to be 0.95, comma 8, comma 2. So pull out the calculator. Inverse norm, 0.95, comma 8, comma 2. And I get 11.3. So I know that if an engine lasts, I should say it like this. The way the question is worded here, what they want you to get from this is, I am 90% sure that an engine that I purchase is going to last between 4.7 years and 11.3 years. I'm very, very confident in that interval, that's how long that engine will last. Oh, that makes sense. Okay, now in this question, we read that the marks on a test are normally distributed with a standard deviation of 12. Kim's mark of 74, so Kim got a mark of 74, and that puts her in the 80th percentile. So she's over here someplace, okay? So here's her mark of 74, and that puts her in the 80th percentile, meaning that she beat 0.8 of the group. We want to find the mean, okay? So what we need to do first of all here is the one relationship that we have that we just got recently here is this. I know that my z-score is equal to x minus the mean over the standard deviation, which means if I multiply that up, the z-score multiplied by the standard deviation is going to be x minus the mean, or the mean is going to equal x minus the z-score multiplied by the standard deviation. So there's my formula for finding the mean, okay, based on the information that I'm giving here. Now what I don't know at this point, okay, I don't know the mean. I know that Kim got 74, I don't know the z-score, but I do know that the standard deviation is 12. But I do have the ability to find the z-score because I know the area. So I know my z-score is going to be, I can get that using the inverse norm, and this is going to be 0.8. And if I want the z-score, all I have to do is give the calculator the information related to the z-score. So, and I do that by saying that the mean is 0 and the standard deviation is 1. So when I go to my calculator and I say, okay, the mean, I want this to be 0.8. Whoops, no, I did that wrong. 0.8. I want the mean to be 0, and I want the standard deviation to be 1. When it does that, when you write it in like that, the response is going to be its z-score. Okay, so this is the number I'm going to get here. Now I'm going to enter this in as 0.84. Okay, I'm going to leave this as 0.84 here. But when I go to my calculator, actually what I'm going to do is I'm going to leave this in here. Okay, so I'm going to make that 74 minus that answer multiplied by the standard deviation 12 here, and we're going to get 63.9. Okay, so the mean here was 63.9. Okay, and in that case here, it doesn't say round to the nearest tenth here, so probably what they're asking for here is really 64% is the mean.